Hello and welcome to another episode of Learning Rust with Good Oxide. Welcome back, Sydney.
Hi, Sebastian.
And what you look at here is our last session with closures. I like this one because I learned so much despite having used closures a million times. It's really useful to imagine that imagine them as the structure that you can call, and then this parameter of self is exactly what explains why we have fn, fn_mat, and fn_once. And now I think the natural thing to do next is to look into threading and see how we use threads and multi-threading and how closures are working in that context. And maybe we learn something new, especially I learned something new as well that I never really dared thinking about. Okay.
Probably I will as well.
Maybe. But, I want to keep your expectations low on this one. So, because just threads, right? What could threads do? So, what do you know about threads in Rust? Like, is Rust doing anything special to threads that hasn't been there before? Or, like, what's the deal there?
Well, I'm guessing that it just has threading implemented with the entire ownership model, right? So you kind of have to make sure that everything is being used by those rules.
Yeah. I mean, sure, it's everywhere, this ownership model. And so far, we have used it without threads at all. And it forced us to write, let's say in practice, it forces you to write better code, and it forces you to rethink certain things. And it applies to threading too, but there's a bit more stuff happening with threading, and that's definitely something we will dig into, we will encounter. Some new traits that we've never seen or heard of before, and why they are present at all, why they're needed in the light of threading. But the cool thing is that this type system that Rust offers in the presence of threading allows you to use concurrency or parallelism, whatever you want to call it, fearlessly. Because the only thing that could possibly happen is a deadlock. Like, people blocking on each other's blocks or something. That's impossible to statically prevent. But everything else is statically prevented, so you can just put threads in there, and if it compiles, it will work. Maybe it deadlocks, but besides that, it will work. And most of the time, it doesn't even do that, the deadlocking. It's amazing. I was writing some software in another programming language that says it's so cool with concurrency, and the first thing I do there is deadlocking, which is, fair, but it's something that happened easily there, and so far in Rust it didn't. I don't know, maybe I'm doing something differently there. So here we go. What do we have? std thread spawn. I think that's all we need to try out everything. So it takes ff, very nicely named stuff here. Ff, that's a what is
Sounds
it?
like a function.
Maybe a function.
Or
Closure. Maybe both. Function could work. Let's see if a function can work. So let's do some work here. I don't know what it returns. Yeah, let's just return nothing and see if we can put that in. It does seem happy. Okay. Let's do some work. Interesting. I would have expected to see the work happening, but apparently that's not the case. Okay. Okay, that also does not do anything.
You maybe have to wait for the thread to actually finish.
Wait is not there. Join is there. Okay. And now we see work. Okay, fair enough. This tells us a few things. Threads by default are free floating and they will not block your program from shutting down. And to me, this was a bit surprising because you think it's the natural way of things for the main thread to wait for the other threads. Like, the main thread is the program, right? So it always has to wait for everything else to finish. But that's not the case. It's actually not a law of nature at all. It's just something that some programming languages or runtime impose on you. In Python, I know that there's the differentiation between daemon threads and non-daemon threads, and I think the daemon ones are the ones that act like this. So they're in the background, but they don't prevent a shutdown. So Python also does something special on top of what is the nature of threads, which means, well, you don't have to wait for them. I will just kill them. The operating system will do that. And Rust doesn't do anything special with them either. So you have to collect them, you can assign them to variables, and then you can do some other work. And in the end, you wait. Okay.
So because you just said collect, does the thread then really only just run when you call join, or does it start running before that? And that just means kind of wait until that's finished.
So does the thread run before I join?
Before you call join, essentially, yeah.
Is it already starting up? Let's see, can we answer the question by looking at the output? No, I mean, we could assume that it only kind of starts when you join here because it actually runs after, right? It's not immediately starting. And this apparently doesn't wait for the thread to start up, right? So the actual work is done a bit later and we can do some other work in the meantime. So this is already done concurrently here. I mean, sure, we could check the documentation, but as a matter of fact, they start right away, but there might be a delay until they start. But as soon as you have this handle, this join handle, you can use that to synchronize with them and basically just wait for them to actually finish, which they might never do depending on how you write that thing. It's also kind of explaining why starting the thread only when you join is not so helpful if that's the only option, because then you can only ever have one thread at a time and you wouldn't want that. So yes, they come up, but there's always a delay. And interestingly, this happens now in parallel. And parallel means, yeah, a whole lot of stuff could be happening that the ownership system will probably prevent. So what about shared, or state? So this is a function. This is stateless essentially. There's no state in it unless the state that is owned by the function. So that's always safe to use. There's no issue. So let's use a closure instead. So this can be more interesting for us as we build out that closure. Also, something that we have just accepted is unwrap. Why do I have to unwrap? I mean, look at this. This join here, or this function doesn't return a result. This just has unit as a result, so nothing. So nothing can happen, right? Why can I possibly, why unwrap? I don't know.
Well, I mean, I guess, yeah, the thread can fail or successfully run, and that's something you catch, but maybe it does return a result, the join at least.
Yeah, let's see what that is. Okay. Thread panicked at oops. Okay, some details omitted. And then thread main panicked at result unwrap, error value any. And that's here. So we have two panic traces now, one from the thread and one from here. And before that, the unwrap here didn't cause a panic. So it looks like this join will have a thread result with this thing that carries the actual the actual error, the actual issue, whatever that is, in a box that hides all the details. It's literally anything in here and some traits that we, I mean, one trait that we didn't see before. Okay. But that's literally for panics, right? So we have to join and handle a potential panic here on the join side. And only if the thread did not panic can we see its output. Right now, the output, let's print the output like we always do. Let's debug print this. Oh yeah, the oops might have to go away here. And now we see unit as an output, and you can imagine that if I put 42 here, we see 42. Or anything else really. Anything you want to return here is going to be passed to the one who joins. And that is something that is also nothing that is inherent to threads, actually. Like this passing of ownership of some value is nothing that threads can do naturally. It's something that Rust actually implements for you by passing it safely through some channel or something like that, some synchronization mechanism that allows this join to happen in the first place, and that is itself used to also pass a value while you're at it, right? So threads, raw threads by themselves, they're actually really, yeah, they're kind of tricky. And you have to be careful. So I'm happy that Rust puts some smartness on top that allows you to get a value out of that thing. Otherwise, yeah, how do you pass values otherwise? Yeah, let's see. How would you pass a value? Like if I wasn't
into the closure, you mean?
Yeah, let's pass values into the closure and then also think of getting them out of there. Return value works, that's fine. We can also try to have mutable state somewhere and see what happens then. So, but one thing at a time. Let's pass values in, huh? Let val be something with copy. Print work, and we just print this. Okay. Function requires argument type to outlive the static lifetime. Oh. To force the closure to take ownership of val and any other reference variables, use the move keyword. So put that here. We've done that once, I think. And now it's happy. And we see 42.
Right. And now this would usually move the variable, but in this case it's copying probably, right?
Yes. Yes, exactly. It's copying because it can, otherwise it would move it. Just standard ownership rules. Always like this. Copy types, they're always copied, not moved. Remember this. This is perfect. So by default, closures, in our case, our val, let's make this, our val would be this, and it's literally a borrowed number. But the borrowed number is living only as long as it lives on the stack in main, but that thread is literally, look, here's main and the stack of main, and it has a certain lifetime, and that thread is entirely decoupled from main, and it lives maybe a little bit longer, probably a bit longer than main even lives, because then as main goes down, the operating system sees, I end, and now I kill all threads, and these live longer than main. Ergo, not long enough to reference something that is on the stack of this thing that soon will go away while I'm still alive. And ownership prevents that from happening. This is why everything that goes in a thread must have the static lifetime. And remember, static means either fully owned or means it's a literal of some sort, like a string literal that is part of the binary data, that is just somewhere that is immutable. So string literals, they're static, for example, by default. This also means, since it should be static, let's try something else. Let's do this. So string literal, what happens here? Look at that, that works. Because these things are static string slices, or static strings. Because they're living, yeah, they're known at compile time, they're just somewhere and can be referenced forever, no matter what. Oh no, wait, sorry. Let's remove move here. Oh, yeah. So I'm lying here, because the lifetime has been reduced, even though this is static as, you know, as a string literal, it's always there. It's only referred to by, or it's only known through this val apparently. We are able to have a static variable here, which also works because the lifetime of this thing is originally static, but it gets reduced if we put it on the stack. So then we put it on the stack somehow, and it just doesn't magically become static again. Interesting. But it works, no move here. Because now, back to our closure, now val is this. And move does this. And that's how you imagine it. And this is why that works. Yeah, nothing more to it. Let's put this back into string from into val. Now let's see a non-copy value. Of course, makes sense. Now if we move this and we try to debug val, you'll see it already has been moved.
Makes sense.
Makes sense. Nothing new there. It all makes sense, interestingly. But this closure thingy really helps. Such a big outcome, such a huge difference this mental model makes. Now, what else is there to learn? Yes, okay, we can pass stuff in, and we know it must have the static lifetime.
So can you then just reference stuff? I mean, I guess the lifetimes then play a very big role, but you should be able to reference stuff from the closure, from within the closure, basically.
But referencing from within the closure, is this, I mean, this is what happens without move, right? And we know this doesn't work because anything on the stack does not live long enough.
Yes.
So can't. But let's say this is something very expensive. Like this is 100 million gigabyte of data, and I want to keep doing something with it in my main thread and maybe in other threads as well. So you want to distribute data, right? Like how do you do that? Let's say we have, let's make this a bit more realistic. We have a vector of numbers, and we want to offload this to multiple threads for processing. So here we want to print the first one, which is a lot of work. Let's make this do this differently. So here we have one thread that does a lot of work with value. Oh, come on. And here we have another thread that uses the other slot that we have here. And this is how we have multi-threading going and high performance printing, something like that. And now for each thread. Yeah, I can totally shadow this, right? I can just use the same name of the thing that I'm iterating, no problem. But maybe we just call it thread to make it a bit less confusing. Thread join. So now we have two threads. As you can see, I just keep them in a vector to be able to join on them later. The joining happens in my order, knowing that some of them, they might already be joined. They might already be done. So in that case, it wouldn't actually block or wait, right? So this is why it doesn't matter if you want to wait for all of them. It doesn't matter if some block you, some don't, because ultimately it will use the same time, same amount of time. Now we have the same issue. We have to move stuff around. But if I move this, then you can already imagine what's happening. I move the vector here. I can't use it here anymore. And it tells you just that. But that defeats the purpose. How can I do multi-threading in Rust if that I can't even share data? I want to share data. Read only, right? It's not, it should be safe. There can be any amount of readers. We know that. It should allow me that, but it doesn't because of that silly static lifetime. So silly. Because look, I join here, right? It can't outlive. Like it can't live longer. Why is it static nonetheless? I don't understand. Yeah, it's just conservative typing, because you don't know if people join or not, and you can't prove it at runtime. Sorry, you can't prove it at compile time. I mean, at least currently you can't.
Okay.
Yeah, so you would have to be able, would have to follow the threads. Here it's kind of easy, right? Here you just see it right away, and the compiler can definitely see that too if it wanted to. Then can dynamically change this lifetime requirement to not be static, but to just be thread local, so to say. But it can't. It has to assume the worst case, and it can't dynamically change lifetime. Somebody has to put a lifetime there. Look here, somebody has to write that. And only that is safe for everyone. And this is why we can't do this most obvious thing that would actually work in this case. It would be fine. So this local threading or thread, how is this called? Scoped threading, a thread with a scope that can use the outer scope. It's actually a thing in Rust that you want, and there are crates to do that for you. So there's, for example, Crossbeam that has a scope thread, and the scope thread can do exactly that. You can launch threads within a scope, and you can refer to variables or data that is outside of that scope, and no static lifetime required, because it knows and guarantees that these threads will be shut down in time. And this is why. But the standard thread does not support that. But there are threads that do. And it just needs an extra crate. That's all.
That means then there must be this different way for sending the data in, or does this just not work with plain Rust?
It does not work in safe Rust. So these crates use some unsafe to say, trust me, compiler. They basically change lifetimes. They change lifetimes from static. Sorry, they change the lifetime from the surrounding scope lifetime to static, so that you can move it into the thread knowing that they will join in time. But in theory, that could be an issue if they don't join in time. But they basically just bend the rules using unsafe code. You can do that. But you don't want to do that unless you really know what you're doing, because it's very complicated when you use unsafe in the light of panicking behavior, and wow, it's complicated. Then you have 5 lines of code and you can look at it for an hour and find new things that are wrong with it. It's like staring at C code. It's kind of the same thing, but in Rust you're more aware that it's so dangerous and difficult to get right. So it doesn't work. Cool. We know that. So is there a way in Save Rust to do that? Yes, there is. Let's put moves here because we do need them. Because what we now want to do is shared ownership. So we want to be able to also use that value in the main thread, and we just want to read it. Nothing special here. So multiple readers should be fine. But we have to make sure that no matter who has access to that it will always live long enough. Like I have to have a handle to that thing, and it's kept alive as long as there's somebody referring to it. And that's a runtime property. That's not a compile time thing. This is why we can't do it like this. So what's the kind of data structure you might know that does that thing? Like shared ownership of stuff.
Like a database.
Like
No, I'm not actually sure.
Yeah. Honestly, a database would do it. It's a big hammer for that small nail, but it would do it. There is, we talked about boxes already, and boxes is single ownership, but allows you to move things onto the heap. So what if we could, and that's where it lives forever technically, but the box gives you a lifetime to it, so it's actually removed as the box is discarded. Box is already kind of, it's a pointer type, and box is already something we talked about. So there are other kinds of boxes as well, because that's unique ownership, but there's also shared ownership. What about RC? RC is reference counted box. So it's like a box, put stuff on the heap, but you can have shared ownership to it. So multiple people can have a read-only handle to that data. So reference counted vector should do it, because then it would never go out of scope. Let's try that. RC new.
So it works like a box, basically. It's just a wrapper around the actual thing.
Yes, exactly. And it implements deref, so this thing automatically derefs to the thing inside. So you can use this RC like a vector. You can use .lang, you can push things. It's just like a vector, but it goes through an additional pointer. It goes through the heap first. So it's not on the stack anymore. Now it's on the heap. And we see that something else is a problem now. Oh, look at that. Oh, dude. So RC vec cannot be sent between threads safely. Are you kidding? Okay. Rust doesn't make it easy for you, but Rust forces you to make it safe. Within that closure, the trait send is not implemented for vec. Look how it talks. Within that closure, it gives you this type definition of something with a line number and whatnot. This is a type. And remember, it tells, oops, not here. It tells you that it created a closure like this with a type that is named like that. That's the type name. It's impossible to type that name because you can't ever type it out. You can't spell out that type. It's an anonymous type, but it is a type, and it's exactly this. So within this type, send is not implemented for this. So there is a field here that is now an RC because we move it, right? So it's an RC vec of U32. And send needs to be implemented for everything that wants to cross thread boundaries. So if you want to move things into a thread or out of a thread, you need send. Okay, that's a bit of a, yeah, it's a bit of a mouthful there. Because it's kind of not obvious why that would be, right? Why do you need send? What's the thing about send? I can send stuff anywhere. It's just, you know, so far there was no issue with send. Now it is. I don't know why. So because send, by the way, is a marker trait. So the compiler automatically marks any type with send if every field within that type is send. And by default in Rust, everything that is owned is send. Everything that is a read-only borrow is send. If everything that is borrowed is send. So we can actually share references to things into threads as long as they live long enough. Then you have the static lifetime to deal with again. But at least you don't have to deal with send. And mutable references, they are, I think they're also send if everything inside of them is send, but you only have one of them because it's a mutable reference, and then it moves there again, and then you can't share that across multiple threads. Okay, but this also means that some types, they explicitly say they are not send. And this breaks send for everything that contains that thing. So let's have a look at RC for a moment. And you see it implements not send for every RC. Huh. Okay, so this is where it prevents itself from being moved across a boundary. And why does it do that? Well,
to keep the counted references in check, right? That's what it's doing. It's supposed to stay in one place, live in one place, and that's my guess.
It's close. It's close. The stay in one place, maybe not, but the reference counting is the key to this, because the counter, what is the counter? Is the counter something that counts properly across threads or not? Think about it. I can move the RC into this thread and into this thread. If I could, right? I could do that. And then in there, I make a few clones. I clone this thing around so the ref count goes up. But if you count in a manner that is not thread safe, then the count will go out of sync with reality. Like the threads would just race with each other, and you have a count that does not match the actual count anymore. And then what could happen is that you allocate too early while people still have a reference to it, or the other way around, you never deallocate, something like that, which makes that unsafe to use. Probably many C++ programmers ran into that problem, that they were actually using a thread, some sort of pointer that is counting content, a shared pointer, but it's not thread safe, and nobody told them. So here the compiler tells you in its own way with send, which is really its very own way, because it also doesn't tell you what else to do. It could just tell you what to do, to be honest, because it's a typical error that you see a lot, I guess. So RCs are not thread safe, but there's more to thread safety. You'll see that in a moment. So there's another way of counting. It's called an arc. Arc is atomic reference count. Reference count, atomic reference count. And these atomics, you know it, they count properly even across threads, because low-level synchronization primitives they are. And they must, otherwise you would have trouble using threads at all. So CPUs do have these synchronization mechanisms for you. And now we got a chance. So now this issue is gone. Let's see. But we still have the move issue here. So we move that value here, and then it's not available here anymore. What's going on? What does that mean for this arc?
That it shouldn't be moved?
Well, it means that it is moving. It is not automatically copying itself. It means it's not copy. This thing has to be cloned explicitly because it's expensive to, relatively expensive to clone. Because you have to increment that counter. And now that's an atomic counter. So that definitely is expensive, but also RC will force you to clone it explicitly. It's not copy. Similar to the vector, right? It's nothing new in a way. So now, what do we do to fix this? The only way to get multiple copies, so to say, multiple clones, I might also say.
You have to remove the move.
I have to clone the arc. And then move the clone in. Look at that. So now the next one gets our original handle. See this as a handle. And now we cloned the handle once, and the clone goes into our first thread. Now the original handle is still present and goes into the second thread, and our main thread has an issue. Can't access this one because the last handle was just moved here. So now we clone that again. And this, by the way, clones the handle, not the content, right? Content is here on the heap safely somewhere, and handles boop, 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 relatively cheap compared to what's pointed to. So let val be val clone. And now this compiles. Voila. And what do we see here? Work 42, work 10, so the two threads print something while our main thread also still has access. So now we have shared data and we can essentially do cooperative work faster.
Right.
And you also see here, now we have a non-deterministic program, huh? Look. Now I ran it again and it looks entirely different, the output. 4210, 4210. Okay. Yeah, I was just lucky enough to have a different output there. So it's non-deterministic now, our program. Also, it's not determined exactly. I mean, we handle our results in a certain order, that's okay. But we wouldn't know which one prints first necessarily, but that's okay. Non-determinism. Ah, yeah, there we go. Another version. That's interesting. Wow. Yeah. Okay, cool. That's an arc. So shared ownership is a way to do this. Or if you have a crate, scope threads, which is usually what you do because this is overhead, right? Because now you heap allocate that thing, you move it onto the heap. A lot of extra work. Usually you want to avoid that, even though it doesn't matter in most cases. It really doesn't matter. Forget what I just said. But I say I want to avoid that because I'm just, if I can use, why use the heap if you don't have to? But sometimes you don't have a crate or you don't want to pull it in because compile times, and then you just do it like this and it's also fine. Okay. So what about modifications? So processing data is cool, but what if we want to increment these values? Yeah, first of all, let's try something else. Probably not going to work. Change 40, 52. Let's make that mutable. So can I just mutate this here? Closure style. Oh yeah. I can, but we know it probably copied it, huh? How can
I? Oh yeah, that's right.
Yeah, I mean, yeah, let's check that. Let's print. Let's debug change here. Oh, let me also never read unused imports. I'll fix that. Unused assignments. Everything unused is okay. Okay, so change is still 52 and not 62 like we would expect. Makes sense. So doesn't actually share it right now. How could I force it to share it? I mean, at least try. Like, this should be a reference. Like, sure, this has to be owned somewhere, so that has to stay. Can I do this? I can. So now I got a reference to 52. And now I have to dereference it, also fine. And now we get the lifetime issue again. And this kind of thing you can do with a scope thread, which shows you how interesting scope thread are. Like, it makes it so easy and more native. Because of course I wouldn't be able to do the same thing in the second thread. Because mutable borrows, they are moving and not, yeah. Here, use of moved value. Fine. That is expected, but the static lifetime really is is killing our party. Makes it hard. Oops. Yeah, so an arc alone would work. We already do know that. But can arcs allow us to change stuff? Let's see. Let's just do it. So for that, the arc needs to own the thing. So now we pack our number onto the heap. That's an expensive number now. Very expensive. And now this is an issue, which before really wasn't. Cannot assign to data in an arc. Okay, that's a nice message. The trait deref mud is required to modify through a dereference, but it's not implemented for arc. Okay.
So it's simply not possible.
Simply not possible. Or is it? So, sure, we want to be able to mutate something that can, in a multi-threaded environment, and for that, you probably, I mean, yeah. So this is read only here. Oh, I don't know what I'm talking about. Let's just throw mutex in. I actually don't know right now, except that sure, deref mud you want and you don't have it in an arc. So arcs are read only. Everything inside of an arc is read only. It's a shared borrow, if you so will, and that's fine usually. But you can share something that then allows you to obtain a mutable borrow through an immutable borrow. So you can dereference that arc read in a read-only fashion to get a read-only view on that mutex, and then you can tell that mutex to give me a mutable version of what's inside of that mutex. So deref and then deref mud. So first, to do that, we have to lock it. And because stuff can go wrong with these kind of standard library locks, unfortunately, there's a crate that doesn't have that issue, by the way. Parking lot, it's called. Really remember that. I use parking lot a lot because it's just better than a standard library. I mean, in every way, it's better. So you don't want to use the standard library mutexes unless you have to for some reason. But for they fulfill the same purpose. But they can fail to lock something. Locking blocks until you obtain the lock. So in theory, that should never be able to fail. But in this case, it is able to fail. And then, in theory, we should be able to deref mud that thing to increment it. We should also be able to do this, which is just a short form of deref mud. Okay. And now we have the move issue again that we can fix by cloning change, which is just cloning the arc. By the way, many people don't write it like this because the arc is this thing that automatically derefs or Rust's automatic dereffing is working for us here. This is why we can, through an arc, use things the way we would use the thing inside. However, if there's ambiguity, like my vector, it implements clone too, right? So if I say val clone, it's not so obvious whether you clone the arc that is outside or the thing that is inside. I just know that you do clone what's on the outside. If it implements a trait that is on the arc, you call that outer trait always. It doesn't dereference it. But if there is no such thing, the compiler will dereference it for you, and then you call what's inside. So many people also do it like this. They say arc clone, and then just pass a borrow to the value, because that makes clear that you call the arc clone. And that's a method, right? This clone on arc, it's just a method that takes its first parameter in arc, that borrowed arc. And you can automatically call that through that dot syntax here, or you can always just call it like a function that it is. This is just syntactic sugar. So people do this to just explicitly choose which clone to call. Arc clone, please. You couldn't call vec clone on this anyway, because that's not a vec. Or is it? Does it automatically deref stuff? Actually, I don't know. Let's see. Oh yeah, it is automatically derefing this, so that also works. Because this...
Well, that's not confusing at all.
That's not confusing at all. This is doing that under the hood, you know? This derefs the arc, then comes out a mutex that you borrow, and then that comes out a vector. That vector you borrow, and then you pass it into vec clone. Of course that works. Not confusing at all. First time I do this, by the way. It's fun. It's always easy to explain because, you know, Rust only does one thing automatically or two. So whenever some magic happens, you know, is it this? Is it that? If not, then usually it explains. It's quite amazing how if you use the right, like if you have the right abstractions, that a small little thing can be so powerful throughout the language. It's incredible. I think this shows you that your design is correct when you can do this kind of stuff. All right. So we arc clone this thing and we arc clone the change, and now it works. Does it? Debug print. Where's my debug print here? Change. A mutex with data 52. That's wrong.
Oh yeah, that's because it's printing before you're joining, right?
Yeah. It's not yet done. It's not yet done. Okay. So now non-determinism races all over the place. The typical thing. Okay, now print 62. Thread is definitely done. Cool. Jeez, already difficult. And that seems easy enough. There is another thing, another trait that I thought would come up, and I wonder I can make it come up. Let's see if we see it here. No, here we only have send. So as long as we can send something and it's static, we can run it. We also see FN1s here, right? This kind of implies we move the closure itself. Mm-hmm. But what if I don't want to move the closure itself? Can I do that? Huh. No, maybe I'm saying the wrong thing. Let me just search for something. No. But here we have some documentation. Let's see. As the reminder, the send marker trait expresses that it's safe to be passed from thread to thread. Sync expresses that it is safe to have a reference be passed from thread to thread. Okay. So send means we move ownership from a thread to another thread. And sync, which we didn't run into, means it's safe to pass references to a different thread. So yes, let's try that. So what about this one here? Mutex is fine, but there's another version that you can do that you can use in a single threaded environment that is called a ref cell. So mutex is interior mutability for you, which means that through a read-only borrow, we get a mutable reference to the content. So this is the trick here. This read only, this shared, or this borrow, that's what makes all of this possible. When you have mutability in there, things break down, things get much harder, but locks allow you to, at runtime, validate that there's only one writer to the content of the lock, of the mutex, and thus it's safe to edit it. And while your mutex guard is held, you are the only one who's editing that data in that moment. So in a single-threaded environment, you use a ref cell, which works very similarly. I think it doesn't call it lock, but it calls it borrow mut. And borrow mut similarly takes a read-only borrow or shared borrow and returns some sort of guard that gives you access to the content through deref mut. So let's see if that works. So far, okay, something is wrong. Okay. Ref cell cannot be shared between threads safely. Ah, there we go, finally. The trait sync is not implemented. So why is send and sync important? Okay, I tried to get it together. Bear with me. So we know that any value, actually that's not true. I was about to say that any value can be made send by wrapping it into an arc. And that's actually what happens. So now our value is send, even though it's a ref cell, which is not sync. Because think about it, this ref cell, it doesn't actually, it only works within a single thread. But when multiple people at the same time try to access it, then the whole bookkeeping mechanism for mutability doesn't work anymore. Because it doesn't use atomics and whatever is needed to make it work within threads, which makes it faster, but also not useful for threads. This is why this thing here explicitly implements or does not implement sync. So like RC before saying not sync and not send, this says not sync. And this prevents it to be used even though it's sent. It can't be sync. The whole thing is not sync anymore. But now the question, why do I only see send here? I would expect to see send and sync somehow. This is confusing to me, because apparently the bound here doesn't mention sync. So why is sync a problem now? Is this magic? Is this some compiler hack that just works because they wanted it to work? Or is this, what is this?
I'm not actually sure, but it must be coming from somewhere else then.
Yeah. I would have hoped that send requires sync, so that it's more like send and sync, they go together, but they don't. And because it requires of the requirement of impl send for arc ref cell. Required because it appears in this type. Okay, so this is kind of the hint, I guess. This arc has send, and that send seems to implicitly require sync or somehow pull it in. Not quite sure about that. Actually don't know. Sync, is it mentioned here somewhere?
I mean, could it be some kind of automatic implementation, like for implement sync for everything that implements send or something like that? And then there's explicit do not implement sync somewhere.
Yeah, I mean, definitely, these are auto traits, but I would have expected something like this. F is send plus sync, you know, because you can combine these. But that's not the case here. So I don't really know, like this is how I write that stuff. if I want perfectly thread-safe things, or if I want to move, use function pointers across threads safely, I have to mark them send and sync as well. And apparently this is somehow part of what's meant with send. But it's not really... Okay, that precise definition.
Magic after all.
Yeah. So the precise definition is a type T is sync if and only if a borrowed T is sent. In other words, if there is no possibility of undefined behavior, including data races when passing a borrowed T references between threads. Surprising consequence, okay. Aha, interesting. A borrow to a mutable borrow becomes immutable. Okay. Interior mutability, okay, we know that. Non-thread safe versions, cell and ref cell, we tried that. Yeah. These methods perform no synchronization, therefore are not sync. We have seen that implementation of not sync for ref cell. Interesting, huh? That they use non-sync here as example, even though we were told that this is not sent. Because it is not sent, right? But it's also not sync. So sync is really the thing that prevents you from moving references to something, I think. So that's my explanation somehow, but actually I'm more confused than I was before. I have a good mental model, or a working mental model for send and sync. I also know that sync is for borrows, but somehow, yeah, it's a bit different than what I expected here. Maybe one day I understand where the sync requirement is coming from that is magically not mentioned here. Strange. Still not there. Oh, maybe it's an FN1 somehow. No. Also not. Maybe FN1s, because it's supposed to be all owned, is sync because of that. And then if something, when you try to put something in that isn't sync because of this, then the whole closure loses its syncness and thus isn't FN1s anymore. Maybe something like that. Okay. Then, long story short, we can't do this. We need to use thread safe versions because only they are sync. That even makes sense. I hoped I would have a better example and maybe less confusion with this one, but it's okay. Git Oxide uses this quite intensively, by the way, when it comes to pack processing, because that's always multi-threaded, and sometimes this uses a thread pool of sorts, which has static lifetimes as well. So then functions can be passed in by the user, and they are required using their trait bounds to be sent and sync because they're just passed to multiple threads. So you have to be very careful. I mean, whatever is inside that function is ever just local to that function. So no own state, stateless, or whatever it does is synchronized in case it wants to access other data or something like that. Which you can define with these traits, and you need to, otherwise it will just not, you will just not be able to use it in a threaded context. So can't go wrong. That's the good thing. The compiler will tell you need sync, need send, need that, blah, and you add it to the trait bounds so that you finally get a closure that works in that context. Okay, let me put a mutex back here, lock it again, and everything should compile. And that's it. That is probably enough for threads. And that's all there is to it, really. It's these two bounds that make thread safety possible, send and sync.
And then args for creating the pointer or the reference, and the mutex for basically shared mutability or shared references.
Synchronized mutation using mutexes and shared ownership using args. Thread safe shared ownership. Shared ownership is RC, thread safe shared ownership is arg, and thread safe interior mutability is mutex. Non-thread safe interior mutability is ref cell or cell. Yeah, there's a nice table where you can see all these properties. I don't have it anymore. I saw it sometime on Reddit, but that's really helpful. But also it kind of makes sense once you did it a few times. And in a way, just start with the non-thread safe versions of these things if you need shared ownership or if you need interior mutability. And let the compiler tell you that you need different things like thread safe versions of it. That should be it. Also, I think my recommendation here is, next to the ownership system of Rust, definitely know ways around it so that you can move ownership checking to runtime, which is what this is. This is runtime shared ownership, which doesn't need you to borrow things. But shared ownership, that's always read-only, which means that through this, you need interior mutability to make any change, to assure that at any given time, only one writer is present. And only one reader, by the way. That's also enforced. So, sorry, 0 readers while there is one writer, or any amount of readers. So that's also what's enforced through a mutex or a read-write lock or something like that. There's various primitives that do that kind of stuff. And that's all you have to know, because sometimes this allows you to bypass these constraints that at compile time can't be proven. In other words, with Git Oxide and Git repository as the high-level abstractions that people can comfortably use, I use interior mutability all the time because I have to. Because what I'm doing there is not representable anymore with compile time ownership checking. And you need shared ownership to some extent. You need interior mutability, and you need awareness of what goes on where, what is thread local interior mutability, what is thread safe interior mutability. And that thread safe interior mutability you want to keep to a minimum, because that slows all threads down, because they have to synchronize around this resource. And the thread local interior mutability, even though you need it, is something you can then maximize, so to say, because you need this interior mutability, but also you don't want it thread safe. You want it per thread, which has various benefits also when it comes to performance and local caches that are then specialized to each thread, depending on their actual workload, instead of sharing some central resource that then keeps trashing caches and has to deal with 20 different users that do very different things. And then what do? You probably serve everyone badly. Whereas the system that Git Oxide is using is that there is a shared resource, but that's only accessed rarely, whereas most of the work is happening in thread local ones that are specialized caches specifically for the workload of the particular thread, because these are created as the work is happening and thus are very specialized to that particular kind of work, which is pretty awesome. And Git Oxide, and I really have to wrap it up, but it's super interesting, I think. Git Oxide has a bunch of caches because you need a ton of caches to accelerate certain, or to reduce waste essentially. Pack caches, object caches, to name 2, which are always needed to accelerate object access. And then you also need access to actually mapped packs and pack indices. And also these are very, yeah, are very expensive, so to say, to maintain, and are limited because it's a system resource that you're using there with the memory map. So all that has to be properly handled, but I think Git Oxide does it in a way that I wouldn't be surprised if ultimately that thing will be faster than it was before, and object access will actually be even faster than it was before because of these now localized caches. And I can't wait to actually show that off and say, okay, there's another 10%, there's another 20%. Who knows how much it's going to be? I will say more once I know more. Well, that's it for today. Thanks a lot for watching.
Cool. Thank you very much.
And thanks a lot for being here. See you next time. Bye-bye.
Bye-bye.